Okay, welcome. EE123, lecture 16. Woo! Woo! Monday. Today, we're going to talk about resampling. Actually, if you think of some of the operations that you're going to be doing, like people do with DSP, resampling is one of the very most common ones because you always need to change rates of signals that you capture. You capture them to a higher rate, you need to downsample to do some processing, then you need to adjust for some A to D, that some hardware, for example. The hardware on your computer is usually doesn't accept any type of rates that comes in. Like if you look at the device, the audio device on your computer, it's going to be set to, I don't know, 8,192 or 16,000 whatever samples, or 21,050 hertz, or 44.1 kilohertz, or 48. But there's somewhere in between, and so sometimes you have to actually, in order to play it, you have to resample it in order to do this. If you have some clock skew between two different type of machines, you record something on one machine, but it's not exactly the same on another machine. It's very, very common, especially if you buy one of these cheap audio devices. And so you have to do some conversion in order to correct for these clock skews. So you have to resample your signal. The other reason that you should be paying attention here, apart from really being useful, is that this is a source of infinite number of questions that you can ask on exams. They're so cute and weird and tricky. So, yeah, pay attention. So last time we talked about discrete time processing of continuous time signal. We also did continuous time processing of discrete time signals, and it was like, well, what is that? Why are we actually doing this? Well, the reason we did this is because there's some systems that when you apply them in discrete time, it's not obvious what they do, but once you consider their continuous time analog, no pun intended, then it's pretty obvious. For example, this half sample or a partial sample delay. I want to mention, by the way, this website called rtlsdr.com. So you have these RTL-SDRs. This is a good place for a resource to look. They post different articles that people write. It's kind of aggregate of various posts by other sites. But as always, there's something interesting about this RTL-SDR. People do all sorts of pretty cool stuff to do using these devices. So I would recommend looking at this. The other thing that it has that is really, really useful is the Signal ID Wiki. And I kind of showed this before, but if you want to look at different type of signals, then that's a place where you can identify what you're actually looking at. Okay. Great. Uh-huh. And one last time. Yeah. Okay. So today we're going to talk about two various things, but one of them is, the first one is downsampling, and that'll be really useful for the lab. By the way, we're going to post lab 3 part 2 probably later today. We ironed a lot of the things. Now it's much nicer, and we're going to post it today. But in order to do lab 3 part 2, you have to design filters, which we haven't covered yet. So we're going to tell you how to do it. But details about, why do you choose one of these, we're going to talk about later. The other thing is you're going to do is, it's a chicken and egg thing. Like you can't do anything without a filter. But filter design, you have to talk about this, but it's obviously where things come. But it's a tool that you're going to be using. The other thing you're going to do is a lot of resampling or downsampling, and so on and so forth. And so this is very useful what we're going to cover today for the lab. Again, from the reason that you capture data in the RTL-SDR that's way faster than you need afterwards to play it. And so you need to change the rate in order to play it appropriately. So what is really downsampling from a conceptual point of view? is it? So it's kind of throwing away samples, so it's reducing the rate. So once you have a digital signal, let's say it's a representation of the analog domain, right? So it's a sampled version of the analog domain. What does it mean to downsample it? Let's say you have a continuous time signal, we sampled, now it's discrete, and we are going to downsample it. What does it mean with right, sampling it at a different rate in the analog domain. That's the equivalence. So effectively, we are changing the rate of our measurements as if we've sampled at a different rate in the analog domain. So it's really much like continuous to digital conversion in some way, because now we're resampling or sampling our discrete signal. So it's kind of like this. And so in that case, you should get similar effect like aliasing. And you have to mitigate with it by using anti-aliasing filters when you downsample the signal. And if you think of the case where you have a really finely sampled signal, let's say you sample the signal at, 1,000,000 times its Nyquist rate. It's almost continuous for all practical purposes, right? So in that case, downsampling would be much like sampling. Okay, so just from an analogy point of view, the finer samples you have, in fact, then downsampling would be very much like sampling. And so what we're going to do now is going to talk about how to change the rate of discrete time signal, because let's say we sampled at 240 kilohertz using our RTL SDR, and then we demodulated something like FM, and we want to go down into 48 kilohertz in order to play it on our speaker, on the sound system on the computer, because that's what it would accept. It would not accept anything different or higher. It would not accept 240 kilohertz for sure. So what do you do then? And so we don't want to. One thing we could do is we could maybe play it using RF. I don't know, and then sample it again. It doesn't make sense to go through the analog. Right? It doesn't make sense. So we want to do all those operations in discrete time. Okay. You ready? Okay. So the downsampling operation is modeled in the following way, and I'm going to introduce some systems that we've kind of seen before, but we're going to analyze them more carefully now. So you've got x of n coming in. What is x of n? X of n is x sub c evaluated n times t, right? So it has a relationship to the original continuous time signal. And the thing is, it doesn't have to come up from a continuous domain, but we're going to look at this because it's easier to conceptualize what's actually going on. What happens if I just throw away? So I put it through what's called a compressor. Compressor, what it does, it takes every mth sample, okay, and throw the rest away. Is that shift invariant? Time invariant? No, because it compresses time. Is that memoryless? No, you have to have memory. Is that linear? It's linear, but it's not shift invariant. Okay? All right. So you get at the end a decimated signal, x sub d. So we're going to use the sub d as the decimated one. And there's the difference between downsampling and decimation, and you'll see what's the difference. But this is decimation. And the value then is going to be x of n times capital M. Okay? So basically we take every mth sample. But that is also related to x sub c n times m, capital M times capital T, which is basically as if I sampled the continuous time at a rate which is t prime, or m times t. Right? I just skipped mth sample. Right? So my rate now is m times lower. Okay, so now there's going to be a lot of derivations. So I'm going to pretend I'm going to write on the board in the sense that I'm going to just go slowly through them so you can follow. Okay, so I'm just pretending. Okay, look at my handwriting, how lovely it is. Yeah, and I can put serifs and all this stuff. It's pretty, right? That's great. Okay, so what I'm going to do now is I want to find the relationship between x e to j omega and the decimated one and see what's actually going on. And I'm going to do that through x sub c. Okay, so through the Fourier transform of the continuous one. Okay, so I want to find the relationship between the DTFT of this one and the DTFT of this one through the continuous time Fourier transform of the original signal. So what is if you remember from last time, or maybe the last two times, what is the Fourier, how is the DTFT related to the continuous Fourier transform of the continuous signal? Remember, it's basically replicas, right? So this replication thing that's going on over there. And so we have this, when we have just omegas, from the continuous time, we have to have some t, so that represents the sampling rate. So what is it? It's 1 over capital T. So that's the scaling. The fact that I subsample, when I sample, there is some scaling associated with this. And then I've got effectively replicas of the spectrum of x sub c. And how often those replicas occur? Well, the replicas occur every 2 pi over t times integer. Okay, so sampling gave me these replications. Okay, can I move on? Okay, sampling gives me replications. Now, what about x sub d? X sub d e to j omega. Well, now the replications happen not at 2 pi over t as before, but it happens at 2 pi over mt. Because now I've got my sampling rate has changed. So I have m times longer time samples, but mth the rate. So my spectrum now replicates more on top of each other. Okay? So the distance between replication is not 2 pi over t, is actually 2 pi over mt. And if m equals 1, that's the same thing. If m equals 2, then I've got twice the aliasing. My bandwidth is actually reduced in the sense that I've got to get more replicas. At 3, I'm just more finely going to replicate, and so on and so forth. Okay. Okay. So now I need to find kind of a nice relationship between these. So I have these two. Now I'd like to bypass the use of this x sub c. I want to actually find what is the relationship between this and this directly. So I want to go from x e to j omega to x sub d e to j omega without going through x sub c. So I want to create here something that looks like something here. Okay? So I'm going to massage this equation so that it looks like something here, so I can substitute by a function of x e to j omega. Okay? That's what I want to do. And so just from an intuitive point of view, if you think about this, if I get more finer replication in the when I do the continuous time, what am I going to get in the discrete time? Probably I'm going to get some replication in the discrete time too. Okay? That's from an intuitive point of view. So what I'm going to do now, I sum here over k. Instead of summing it over k, I'm going to split into two sums. I'm going to sum over r, and I'm going to sum over I. This is like, if you think about it, it's like two counters. One of them is hours, and one of them is minutes. Okay? And I'm going to sum, therefore, r from minus infinity to infinity, and then I'm going to sum I from 0 to m minus 1. Okay? So those will give me exactly the same sum, but split into two counters. The reason I'm doing this is because if I sum over r that way and sum over I that way, I will have then a representation that looks something like this. And then on top of that, another sum. Okay, that's kind of the idea. Okay, so bear with me now. Okay, so x sub d e to j omega is equal to this, right? So replicas every mt. Okay, 1 over mt. Now I'm going to split the sums. So I'm summing over I equals 0 to m minus 1, and I have to divide by 1 over m. And I'm summing over r from minus infinity to infinity of 1 over t. And when I split the sum over k into I and r, now when I substituted, if I remember, when I substituted k into r times m plus I, okay? So here the m goes away from the bottom. Okay. So what I have here now is something that for a constant I, for just some I, let's say I equals 0, then I've got some replication over 2 pi over t. I have a replication of my original spectrum over 2 pi over t. That is very similar, if you replicate it every 2 pi over t, that is similar to the case of x, e to j omega. It is replicated every 2 pi over t. So now it kind of looks similar. And if you stare at this long enough, you'll see that, in fact, this is exactly, if you write just this part, if you just write this part, for a particular I, if I sum over all these r's, I will get x e to the j omega over capital M minus 2 pi over m times I. Do you want to see it? Okay. Yeah, no, second. No, second. What? Sound travels faster than light here. Yeah, that's right. Okay. So if you stare at what x e to j omega is, and then you put instead omega divided by m and then shifted by 2 pi over m times I, if you put that here, you'll get exactly that. Okay, if I substitute this variable instead of omega here, then I will get exactly this expression. Okay? And so if this is x e to the j omega, let me get rid of this. So if this is x e to the j omega over m minus 2 pi over I, so on and so forth, then now I'm going to sum over I from 0 to m minus 1 over that. Okay, so now I've got 1 over m. So x sub d e to the j omega is 1 over m, sum of I equals 0 to I minus 1, x e to the j omega over m minus 2 pi over m. So now I have the relationship between my original x. And I see there's two things that are happening here. One is that my spectrum is stretched by a factor of m. The other thing is that it's going to be replicated m times. Okay? So my spectrum is stretched by a factor of m, and it's going to be replicated m times. At shifts that are 2 pi over m times some integer. Let's see what it actually is looking at. So if I have a spectrum that looks like this, this is x of this is x e to the j omega. Okay? That's a spectrum, and the spectrum covers it's 0 between pi over 2 and pi. It's 0 between pi over 2 and pi. So what is actually going on? The first thing I'm going to do is I'm going to scale, and let's say now I set m to be equal 2. So just downsample by a factor of 2. If m is equal to, I need to scale my spectrum by a factor of 2. And then I'm going to be stretching it, replicating it twice. Okay? So if I scale it over a factor of 2, it's going to look like this. It's scaled, right? It's going to go from minus pi to pi, and then from minus, what is this? 2 pi, so from, this is pi, this is 3 pi. 3 pi to 5 pi, and so on and so forth. Now here's the thing. If I just scale by a factor of 2, it doesn't work because this cannot be a DTFT. Because a DTFT is periodic with 2 pi. So it cannot be, right? So it's not enough to scale by a factor of 2. Okay. So I scale by a factor of 2, and that's for I equals 0. What about, I need to then add the replica at I equal 1. And a replica at I equal 1, it shifts by 2 pi over 2. Okay? And if I do that, then it looks like this. So now it actually looks like a DTFT. Okay? And so now my spectrum covers the entire digital spectrum. Okay? Does this make sense? Now, it kind of made sense because if I would have sampled a signal that was band limited at half the rate, so if I sample it at a certain rate and I've got like a bandwidth of pi over 2 left on both sides, if I would have sampled it at half the rate, I wouldn't get aliasing, and it would cover minus pi to pi. Take a look at this. I'm going to go to the board, and I'm going to look for something to write on. Let's say I sample something at, instead of Nyquist rate, I would sample it as twice the Nyquist rate. So my signal would then represented between right? If I sample something at twice the rate, it's going to have a spectrum that looks like this. If I'm going to sample it at the Nyquist rate, it's going to have a spectrum that looks like this. What did I get here? I got here exactly as if I sampled it at half the rate. Questions?
This only applies to integer downsampling?
Yes.
Is this easily modifiable to work with fractional downsampling?
We'll talk about fractional downsampling once we talk about upsampling. Yeah. Yeah.
Why do we scale the
The scale is scaled because it's 1 over m. That comes out of whatever. The truth is that if you sample at t times m, then you would have that scaling as well, right? Okay. So here's another example. Let's say now I take this spectrum and I decimate it by a factor of 3. Okay. If I decimate it by a factor of 3, now first I scale it by a factor of 3. So now it leaks beyond pi. And now I'm going to replicate it 3 times. Okay, it has 3 replicas. Now I've got aliasing going on. And it perfectly makes sense because if I sampled it at a lower rate from the original, lower than Nyquist rate, I would have gotten aliasing. So the question is, if I want to avoid aliasing, what do I do? Anti-aliasing in the discrete domain. Apply anti-aliasing filter in the discrete domain. How much? What's the cutoff? Well, the cutoff is going to be pi over m because that's how much I'm going to be sampling. I'm going to guarantee that whatever was within pi over m is now going to be stretched to full pi. Okay, in the digital frequencies. In this case, when I take a filter that's now pi over 3. Okay? I cut off whatever would have been aliased. Now it's cut off. And now, when I do the stretching and replication, I'm not going to get aliasing. I'm going to cut off my signal, right, the high frequencies. But this has to be because I cannot represent high frequencies at a lower rate. It doesn't. That just doesn't work. Right? That rate doesn't support these type of high frequencies. So I have to either get rid of them or let them alias. Does this make sense? Any questions? Before we move to the upsampling case. So just swallow this. This is exactly like sampling, right? Only now we just get 2 replicas because we downsample by a factor of 2. So we get these 2 replicas, stretching and getting 2 replicas. The other way of thinking about it is you can say, well, I'm not going to say anything. I'm not going to confuse you. I think of it slightly differently, but it doesn't matter. I'll say it anyway. Basically, think of it as whatever your spectrum has right now, you just stretch it, and whatever goes above pi, like beyond pi, right, that replicates back in. Okay? Whatever goes beyond pi over here shows up at this side. And whatever goes out beyond minus pi shows up at the other side. That's another way of thinking about it. Okay? Okay. So now let's talk about, yes?
Is there ever a case where you would prefer to let the high frequencies alias instead of using an anti-aliasing filter?
Interesting. Yes. When we're going to do, if you want to do filter banks, so split your signal into multiple frequency bands, sometimes you are going to allow some aliasing, but because you're going to split into high frequencies and low frequencies, like in wavelets, for example, and then downsample, you're going to get some aliasing. But as it turns out, when you construct the signal back, that aliasing is going to cancel. And we're going to talk about it later when we talk about filter banks. Okay, yes, there is a reason, sometimes when you want to do, when you want to get some aliasing. But, it's not it's a result of, okay, yes, we're going to do it because we can never really get a perfect low-pass filter. So there is going to be some aliasing. Maybe you want to minimize it. And if there is some aliasing, maybe if we do a multi-channel or a multi-rate type of analysis, we can then cancel it back. Okay? But obviously, it's not a desirable thing. Okay. So upsampling is very much like downsampling was an analog to digital conversion, or analog to continuous time to digital conversion. Upsampling is the opposite. It's much like digital to continuous time conversion. Kind of. Again, not exactly. There's a lot of similarities to this. So if you think of upsampling by a lot, okay, if I take some discrete time signal and I upsample it by trillion, billion, 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 trillion, trillion, billion, billion, trillion, billion times, it's going to be pretty continuous, right? Okay? Kind of. So if you recall the D to C model, right? The digital to continuous time model, we took X of n and we created X of S of t. That's the impulsive version. And then from that, we filtered to get X of C of t. Remember that? Remember that? Please remember that. This is like basic. X of S is the impulsive version, remember? So from digital to analog, or from the digital to continuous time, discrete to continuous time, we converted X of n to X of S, and then filtered with a low-pass filter. That's exactly what we're going to do now in the discrete domain. So we're going to approximate X of S of t by placing zeros between samples. And now you've got these delta, like discrete impulses. And then we're going to convolve with a sink, which is a low-pass filter, to obtain X of C of t, but this is really just a upsampled version of X of n. So it's similar, same, but different. There's a lot of things that could happen, again, when you do this. And we're going to analyze it right now. So remember, x of n is like x of c times n times t. Now we're going to expand it. Oh, sorry. This is the new rate that we want to do. Is that right? Yes. Oh, God. Yes. Oh, boy. Thank you. I thought I saw everything. Man, it just amazes me how still I have all these bugs. So this money is well spent. We're spent. Lower x. And remind me, do you have already? Oh, you got some. $4 now. It's pretty good. You buy yourself a coffee or something. Okay. That's for me to remember next time. Okay. So now the rate is changed where now we're going to sample at t over L, where L is an integer. And you want to obtain x of I, which is the interpolated one. I is for interpolation, from x of n in 2 steps. First, we're going to generate the expanded version of x. That's kind of like generating x of s. Right? So the similar impulsive version of it. Okay, so x of b is going to be x of n over L, where n equals 0, plus minus L, plus minus 2L, and so on and so forth, and otherwise 0. Basically, what it does is takes x of n and creates a signal for L equal 2, creates this, puts zeros in between. That's another way of writing it. Okay, it puts zeros in between. So this kind of looks like impulsive now. And if I would have put a trillion, billion, trillion, billion number of zeros in between those samples, it would look like really like x of s. Now what I'm going to do is I'm going to obtain x sub I from x sub e by band-limited interpolation. So I'm going to convolve by a discrete sinc over n over L. So I'm going to place a continuous time sinc over those samples that are sampled at n over L. And as it turns out, it's going to look like this. So n over L will have 0 crossings exactly over the samples of this x sub e. And then I'm going to evaluate what is the value over here. And I'm going to do that only in a discrete domain, right? Basically, it's just discrete convolution with sinc of n over L. So if I do this convolution, I will get samples in between, which corresponds to as if I took my continuous time signal and resampled it over those points. Yeah. I'll get to that in a second. That's a really good point. Right, I could have done a linear. I could also do the 0 order hold. Right, nearest neighbor. Right, I can do spline. All of these are going to have certain implications about what's going to happen to your signal. Okay, and there might be better than doing this. If your original signal was not band limited and you got some aliasing, or maybe you got rid of some samples. But if we're considering band-limited signals, that there's no aliasing in the original signal, we want to resample it, and we consider, well, that was band-limited, then actually doing this is the best. This would work perfectly. But there might be a good reason to do linear interpolation. For example, if my original signal is actually piecewise linear. But that's something else, okay? But I'll tell you well, let's look at what's actually going to go. We're going to analyze that case too. So in the upsampling case, x sub I of n is equal to x sub e of n convolved with sinc n over L. Okay? So really, what is x sub e? X sub e of n is a kind of a convolution with a train of these shifted deltas, discrete deltas. So it's a convolution in the discrete domain with this discrete impulse train, much like we did in x sub s. Right? It's exactly the same thing. You got yourself yes. Sorry. Yeah, so this is basically shifted delta, so this is expanded. So if we want to see what x sub I of n is, really becomes a convolution between x of k sinc of n minus k over L, kl over L. Okay, when you just substitute this with a multiplying by a sinc. And so the frequency domain interpolation of it is that you first take x of n and you put it through an expander of a factor of L. Then that gives you x sub e of n. Then I'm going to do a low-pass filter, and I'm going to put a gain of L to go back. Because this doesn't actually give me this gain. And then I'm going to filter it by pi over L. And I'm going to get x sub I. So the sinc of n over L will give you, if you look at the DTFT, it will have a gain of L. Just because it's not scaled. Okay. So what is the Fourier transform of x sub e of e to j omega? Okay, we want to look at what is the Fourier transform here. The Fourier transform here is, if I just write it down, is the sum of n minus infinity to infinity of x sub e of n e minus j omega. But if I stare at this long enough, I realize that x sub e is non-zero only for n equals ml. ml stands for microlustig. Okay? That's why I picked those n and m. Okay? So it's only non-equal to 0 for n equals ml. So if you have integers of m. So now I can sum over m from minus infinity to infinity of xe m times L of m times L. That's exactly the same thing. And then e minus j omega m times L. But if you stare at this long enough, you realize, wait, this is actually x of m. Right? Because you skip every elf sample. Skipping every elf sample is actually x sub m. Right? If I expanded something by a factor of m, this is really compressing it by a factor of... Sorry, if I expanded something by a factor of L, this is compressing it back by a factor of L. So you get the same thing. So this is x of m. So what I get is just a compression of the frequency domain. So my frequency domain is compressed by a factor of L. Yeah.
For the low-pass filter, is that pi over m or pi over L?
You're good. You guys are good. I'm putting these on purpose. You guys are great. Wow. You're good. And remind me? Finish. Right. That's right. $6. You can buy like a cookie too. Okay. L, not M. Okay, so it's stretched by a factor. So what it does, it compresses the DTFT by a factor of L. So here's an example. What I'm going to do now is I'm going to start with x of c, j omega. And that's the spectrum that I have for that signal. It is limited by what's this letter? Omega over n. Okay. It's limited by omega over n. Then I'm going to sample it by a factor of t. I'm going to sample it at t sampling rate. And I'm going to also sample it at t prime, which is t over L. Okay, so I guess faster. Okay, and I want to show that if I go through here and I'm going to expand it and upsample and expand and filter, I'm going to get back this. So it's as if I went through this is the same as going through here. Okay, that's the idea. So sampling by a factor of t, sampling with t time, will give me a scaling of 1 over t and a signal from minus pi to pi. And t corresponds to the sigma sub n. Now I'm going to look at what is, if I sample at t over L, I'm going to get this type of signal. So I'm going to get L over t amplitude, and then my signal is going to be reach up to pi over L. Okay? Now, when I expand this, first of all, if I look at x of e, what it does, it compresses the spectrum by a factor of L. Okay, so now my spectrum has replicas, but it compresses. So the first replica goes up to pi over L, and then the second replica, and so on and so forth. And now I'm going to take a low-pass filter with an amplitude of L, and then filter it, and then you'll see that it actually gets back to here, right? So it's exactly the same thing. But I did that through the digital domain. Yes. Yeah, of course. There's probably some. Yeah. Yeah. What? What's that?
Is T prime is slower sampling rate?
T prime is.
You're dividing by
Yeah. So like you divide. It's yeah. Right. That's fine.
So it's slower.
It's a faster.
If you're dividing by something that's bigger than 1.
Yeah.
Okay.
Pi over L is bigger than 1. Yeah. Pi over L is smaller, right? So that's fine. L is bigger than 1. Pi over L is that's fine.
Okay. So T prime is less than T.
T prime is less than T, absolutely, because we're sampling faster, higher rate. Right? We're sampling at higher rate. Okay, so now we analyze both downsampling and upsampling. So now you can think of what happens if you want to do resampling at arbitrary rational rate. Right? But before this, what happens practically? And that goes to, who asked the question about the linear interpolation? Who asked the question about the linear interpolation? Okay, great. So often you want to interpolate with simple, more practical filters because convolving with a sink is pretty expensive. So the question is, what happens there? And so, for example, if you want to upsample by a factor of 3 with a linear interpolation, what you do is kind of convolve with the triangle. Okay? Actually, this is L equal 2, but yeah. Great. Oh, no, it's actually L equal 3. Sorry. Well, what's going on with me today? I was right, and once I was right, I was like, I lost confidence. I lost confidence because of you. Okay, so I'm going to interpolate by a factor of 3. What does it mean? It's convolving with a triangle, basically. It's the same thing as convolving with a triangle. Basically, you figure out what is the value at 2 points between these, right? 2 points between these. Now, when you do that, then effectively, I'm going to get, I squeeze my spectrum by a factor of 3. So now, the first replica is going to have a pi over 3 as its higher frequency. Now, if I did a sync interpolation, I would have cropped that, and everything would have been fine. But what happens when you actually do a linear interpolation? Instead of multiplying with a rect, you'll be multiplying with a Fourier transform of a triangle as opposed to a Fourier transform of a sinc. Okay? So effectively, you're going to be filtering it with multiplying by a Fourier transform of a triangle, which is a periodic sinc square. If you do a periodic sinc square, you'll see, yes, it throws away. It does some anti-aliasing. It's like filtering with a bad anti-aliasing filter. Right? So it's going to attenuate these replicas, which are a problem, but it's not going to attenuate them completely. And at the same time, it's also going to create some distortion to your spectrum. Okay? So the result after that will be a spectrum that looks something like the blue. So yeah, it is similar to as if I would have sampled, but it's not perfect. Okay? So that is the trade-off. You're actually doing something that's non-perfect, which is fine, maybe, for your application. Okay? But now you know how to analyze what will be the effect of doing that kind of upsampling, yes?
What is the gain whenever t slope?
Because you scale by a factor of t, right?
Is that like the old word?
Yeah, that's the old sampling rate. That's right. That's right. That's the old sampling rate. Sampling of a factor of t. Now it's t over L. Okay, so you get this kind of a spectrum, which is, yes, it's not great. It's supposed to be triangle, but now it's a little bit distorted and has some aliasing in the high frequencies. Okay. Okay, so now if you want to resample by a non-integer, which is resampling by, as if you're sampling by a new rate, which is t times m over L. So upsample by a factor of L and downsample by a factor of m. What you do first is you upsample by a factor of L, low-pass filter with pi over L, then low-pass filter with pi over m to avoid aliasing, and then downsample by a factor of m. Now, of course, you don't have to do two low passes. You can just take the minimum of these two, right? And so you upsample by a factor of L, low-pass filter by the minimum of this, and then downsample. Okay? And the question is, can you change the order? Can I first downsample and then upsample? Well, not really. So the problem is when you downsample, when downsampling operation loses information. Upsampling doesn't lose information. So if you downsample first, you might low-pass filter the high frequencies, and then when you upsample, you're not going to get them. Okay, that's the issue. So here's an example. L equals 2, M equals 3. And if you sample at a certain rate, this is what you have. If you expand by L over 2, you get this. Now you low-pass filter, so you get that, and then you spread it to get this. Okay? So this is as if I went from here, low-pass filtered, to a certain rate, and then go to this place. Okay? So that works. Okay, so now here's food for thought. That's great. You know how to do rational resampling. That's great. So what if you want to resample by 1.01, or actually 1.00000000000000001? According to this, you have to expand by a factor of 100, or million, billion, trillion times, right, depending on how many points. Then filter by pi over 101, or by this billion thing I just mentioned. And then downsample everything back by 101. Problem. Ka-ching, ka-chin. It's going to cost you memory. It's going to cost you computation. Terrible. But here's the thing. Lots of zeros there. When you expand, lots of zeros. When you then convolve with some sinc, I mean, do you really need to multiply with all these zeros? Do you have to store them maybe? Do you really need to do that? Perhaps not. And so what we're going to talk about next time is how to work around those effects and use what's called multi-rate type of filtering, which when you have upsampling, downsampling operation, you can save a lot of computation by not computing stuff that you're not going to keep. Okay? And this next time. Next time we're going to talk about that. Also going to talk about lab 3. Okay? All right. Thank you very much. See you on Wednesday. Don't forget to register for the ham radio class. They're pretty strict about it, so if you didn't register, you're not going to be able to take it.